Okay, we're about to start. Duje Roje made a very interesting thing here, which I'm not sure how it works, but we managed to pull it off.
Nobody knows.
So he's going to tell us a bit more about what he's doing. So can we get a big round of applause for Duje?
Thanks.
All right.
Okay. Hi, everyone. My name is Duje, and sorry for all the delays and whatever happens. This is normal stuff. When you're working with hardware, it's bound to crash and not work. But what I want to talk to you about today is how you can start using Python for hardware. So just basic prototyping, beginner stuff. And then I want to give you some guidelines on my own experience, what I've learned, as what kind of code design you should use for your hardware. Because there's not a lot of material, well, there's no books on this. So if you want to start using Python for hardware, I recommend something like a Raspberry Pi. This is a single board computer that is Linux based. I'm sure that most of you have heard about this. So if you don't know anything about hardware and electronics, this is an LED, and we're going to be using it. This is a resistor, a potentiometer, and here we have a ADC. This is a module, analog to digital converter, because Raspberry Pi only has digital pins, and we lost connection. Oh, it's back. Okay. So back to the ADC. So if you want to use analog input, you have to use an ADC for Raspberry Pi. More on that later. So this is the code that you would use to blink an LED. If you're coming from software development, this is like your hello world. This is the first program that you learn. And so let's go quickly through it. This is the electronic schematic, how it looks. So you have your Raspberry Pi, and it's connected to an LED, and then it's connected to a resistor, and then to the ground. How the code looks for that, so you have to import some kind of libraries to use the GPO, that's general purpose input output. Those are the pins. Then you have to do some basic setup. This is normal stuff. And then you have an infinite loop. So every kind of device, kind of hardware that you build is going to have an infinite loop. And for blink, it's just you have to turn your LED on, and then you turn it off. And we have some slack as well. Let's give this a go. So maybe we can dim the lights or something, because we have here the Raspberry Pi, and it's connected to this here is the LED, and you should be able to see it blink. So just this is just proof that I'm not making this stuff up. Okay, I hope you can see this. And this is as simple as it gets, really. This is how you start. So now we're going to do a little bit more complicated things. Let's go next. A dimmer. So you just saw there, Boyan, how he dimmed the lights, right? So how does a dimmer work? It sends this kind of signal, so it turns it on and off all the time, and it does this really quickly, so you don't see, your eye doesn't respond, you don't see it blinking, you just see it's either softer or hard or stronger light. And then this should be T on, so this is how long you have your LED on, and then how you have it off. And then the longer you have it on, the stronger the light. It's called a duty cycle. So this here, in this example, you have your 50% duty cycle, that's in the middle, and then 75% is a little bit stronger, 25% is mostly off, and it's a lot softer. What kind of changes do we have to do to our blink LED that we had earlier? So basically, we just have to change these times, right? How long it's going to stay on and how long it's going to stay off. We also have to introduce a little bit more electronics for this. Remember how I said the module ADC? So that's what we have here. We have a potentiometer or a variable resistor that gives us a range from 0 to 5 volts. Now, if you want Raspberry to be able to read this, you need to use an analog to digital converter. And it converts this analog value to a digital value 0 to 32,000. Okay, so we have to, again, import a library for the ADC. And then we have some settings. This is normal. Okay, you have an instance for this library. We have to use a very high frequency, as I mentioned before. And how this works, so the Raspberry reads the analog value from the ADC, and then we calculate how long the LED is going to be on or off, and apply those values in our infinite loop. So let's give that a try. Now, I here have a little knob, so that's a potentiometer, where as I turn it, it's going to go either, so this is like really soft, and then it goes to a bit stronger. So that's basically what you saw there with Boyan when he dims the lights. So that was some kind of basic introduction. But as you start playing with this, so you're prototyping, and it's really fun, but things will start to complicate really, really fast. Especially if you're working professionally, and then you have some guy who's going to say, oh yeah, let's add more things to your system. Let's add a voltage sensor or a current sensor or a fan or a heater or whatever. And then you don't really like that. So based on a true story, this is where I work. So this is a solar smart bench, and it has solar panels, wireless charging, ambient light, cooling systems, USB ports, batteries, Wi-Fi zone, and so on. So the first time I made this code, it was working, right? But then the company decided, let's add a heater, display, air quality sensor, camera, and so on, status reporting, control panel settings, and whatever. So it's gonna, yeah. So your house of cards crashes. So what I've learned is my own 4 pillars of writing hardware code design. So first, scalability. Make your code able to scale, because they will demand that you add more things to the code. Modularity. So as you saw, we use the ADC module there. What if that changes? You have to be prepared for this. Robustness. No matter what you do, the hardware will eventually crash. If you have IoT devices or in a remote location, this might be really, really tricky. And it should be able to easily upgrade. So the first one, scalability. This was our system, right? We have Raspberry Pi, then we have our light, and then what if we want to add a fan or a heater? So the first solution that I used was just kind of, you have your pins and you turn them on and off, and you have that all around the code. And then what if you need to log or add print statements to whenever you're turning on or off a pin? So that would be very difficult in this first solution, because you would have to find wherever in your code you're turning it on and off. But in the solution 2, if you build a class called consumer, and then you have it really easily, you have your turn it on and off, and then if you want to add print statements, you just add them to the functions turn on and off. And this is also very good if you want to add more things to your code, for example, fan or heater, you just create more consumers. So basic stuff. I'm hoping that you understand this. Next off, modularity. So we have our ADC module here, and there are many ADC modules on the market. So you're using this one, and then what happened to me? They declared end of life. So now we have to change in all our products this module, and then the code base is full of it, and then you have to find wherever it is and change it and so on. So that was when I was using solution number 1. So let's compare solution 1 and solution 2. In solution 1, you have the ADC, you're importing the library, and then you create an instance, and this is okay because they're usually declared in one place and then passed around. And then you're using the read ADC, or in the solution 2, I'm using read channel, which is, well, you can expect this to have it all around the code. Again, if you have to make some changes, the solution 2 will be less of a headache. How that works is you basically create a interface, ADC interface, and then each module will be an implementation of this interface. This is better because when you have to change physically the hardware, the module, you just have to add another implementation that's gonna of this interface ADC, and it's gonna be much easier in your code to accommodate, to be prepared for any kind of changes. So the key takeaway here is to create interfaces for components that can change, such as sensors, modules, etc. The third pillar, robustness. Make your code robust. So this is, I'm sure you've seen this kind of messages. It happens to your PC, so it's gonna happen to you as well. This is the example, so how I used the ADC implementation. And then here we have a potential for crashing. Why I say this? Because everywhere where you interface with the hardware is a potential for crashing. Maybe the module is not working or something like that. And then, oh, okay, so you have to encapsulate it and try, except, well, the presentation is kind of, okay. Another thing that you can do to make your system more robust is to add a watchdog timer. So basically one kind of process that's monitoring your main process, and then if something goes wrong, it can reboot the system or maybe even go into a safe mode, which would be something really clean and really something that you're sure is gonna work. So for example, if you have your IoT device in a remote location and then something goes wrong and then your internet connection is down, you cannot longer access this device. And then you have to fly thousands of miles to change it. The fourth thing is make it easy to upgrade. Now, when I say upgrade, what do I mean by that? It should definitely be easy. Don't take as drag and drop to be easy. I'm going to talk more about this. So what does an upgrade actually include? So it includes, so the code needs to change, right? New version of code, sure. Maybe you need to install some packages or uninstall some packages. Maybe there's some database migrations you need to apply or some cleanup. Anyways, so if you have your device somewhere, don't just kind of copy files to it. Just make the device smart so it can upgrade easily, and then it's more than just copying and changing code. Think about, it's a whole process, so you have to install packets, maybe do some database migrations, and so on. What kind of upgrades you can use is, you can use git pull. Maybe you can have your device ask Git if there's a new version and then pull it if there is, and then does the whole process of upgrade, as I mentioned before. Or you can create your own packet using pip or apt-get. And the last thing is, if you don't need to change your whole code, maybe you need to just change a few numbers. Then think about having a configuration file that you can easily upgrade. This is an extra, so testing is just as important with hardware as it was software. And what kind of testing you should do? You should write unit tests, of course. And if you want to test your hardware right there on the spot, you can create a kind of monitoring environment with Flask. Flask is this little framework for if you want to make your Raspberry work as a mini server. And then, so you set up your Raspberry as a server, and then you connect to it with your laptop, and maybe turn some knobs or turn on some lights or something like that if you're testing. I actually had a nice little example here, but unfortunately, I couldn't connect my laptop to the presentation. But basically, how it works, you have your Raspberry as a server, and you have your web browser where you're testing as a client, and you create a socket connection where you can easily test your device. So, if you're thinking about working with hardware, I mean writing code for hardware, what you should expect, it's really fun, because there's actually things moving in front of you when you're writing code. It's hard, although, yeah, you can expect that. It's also prone to some unexplainable errors that you're not sure if it's due to your software or hardware or who knows what. Runtimes errors are the worst. They can render your device unreachable, or if it's a moving device, it can even be dangerous. Okay, so danger of remote devices becoming unreachable. You can also expect to argue with the hardware developers if the error or the bug is due to your software or their hardware. You have to wait a long time for sensors to arrive and stuff like that, and then when they do arrive, you have a very short time to either develop it or burn the sensors, and then you have to wait again. But it's really fun. What I would recommend, so if you want to step up your game with writing writing code for hardware, if you don't know about solid principles, definitely look into that. That should be your starting point. And then you have the book Clean Code. It's like the Bible for writing code, and maybe some design patterns. I really like this book from Head First. And that's it. This is it for me. Thank you.
Thank you very much. Slido, no questions? Let's get some from the audience.
I just want to say you've got the most amazing name I've ever seen in my life.
Really?
Yeah.
It rhymes?
Honestly, yeah.
Thanks. A URL, right?
Yeah, like I wanted to say you have an awesome URL too.
Thanks.
I'll just leave you the microphone because you're a source of questions. Anybody else? All right.
Any kind of technical questions?
Yeah, so how did you set up your local development environment? I guess you didn't write code on Raspberry Pi directly.
No. What I did is I used PyCharm to write code, and then it automatically, as I'm developing it, it automatically copies the code to Raspberry Pi, and then you can also install packets using PyCharm and stuff like that.
Thanks.
Yep.
Here you go.
Hi, I have a question about pull-up and pull-down resistors. Is there an option to use the software ones, or you have to use the actual resistors?
You can, well, depends on what kind of hardware you're using. Some boards, like Raspberry Pi, they have some pull-ups that some you can enable, disable, and stuff like that. But it's best to use your own resistors. This can change, you know. You're using pull-up resistor for I2C communication, and then if you add too many of those modules, maybe those pull-up resistors will add up, and then your whole system won't work. So it's best to use your own if you can.
Okay, thank you.
Yep.
Next one, over there.
What? Do you ship the Raspberry Pi in your product, or it uses a custom board? It depends. We had all kinds of boards that we used in our products, even Raspberry Pi as well, but not like there are some other as well single board computer. Raspberry Pi is more for prototyping, but I mean it's okay. It's pretty stable, but again, it's not really the best option for a product that you're shipping.
Okay, another one from the audience.
Yes.
Yeah. How do you deploy software updates?
Well, we use the Git system. We also had some sort of so we had the whole upgrade process and the code on our own servers, where the benches, where the devices, they talk to our servers, and then if there's a new version, they're gonna download this and then do the whole upgrade process.
So, so the Raspberry Pis are polling the servers and check for new version, and then
Yes.
Okay.
Yes.
How about Docker containers?
That's a really new technology. I haven't really I haven't used it, so I still have to learn this.
Do they even run on Raspberry?
I'm not sure. Maybe. Yeah, I think yeah, it's a Linux-based computer, so it should work.
Thanks.
Yeah. Yes.
So on the slide mentioning updating the software, you said you wrote that there are some security issues with pulling from Git. Could you go into a bit more detail on that?
Yes. So just be careful. So if you're gonna pull from Git, maybe those kind of files should be protected, and then don't have your usernames, passwords, and stuff like that written in plain language, in plain text in your devices.
But is there some way that a third party could exploit it in some other way, like a more subtle way?
I'm not sure. What do you mean?
Well, I don't know. Like if they have access to the device physically, that they could like do something and override what the repository where you're pulling from, or something like that. I don't know.
Yeah, I'm not sure. Actually, I don't know. I'm not sure about that. We haven't had those kind of experience, luckily, I guess. Okay.
Okay, thank you. 2 more minutes. Any other question? There's one on Slido. Okay, how about cluster management? Okay, do you somehow?
Okay. Do you somehow protect your Python source code when shipping the device to the client? Well, it depends. This is we haven't actually. We haven't, but definitely you should. So I'm also a learner, so this is still something that I have to conquer. So there are ways to protect your code and then not ship source code, right? Just the files that you need. Yes? Yes, of course.
Yeah, thank you. In my personal experience working with the Raspberry Pi using Python, a good way to protect the Raspberry Pi, which I also as a learner, just like you, until up now realized would be good, is like when the device is physically available to the client, like he could connect just to the device, to a monitor, and he could see the content, because it's a simple computer, just like any other. A good way would be like writing a script which runs as in the background, like systemctl, and you make it so that you only can access the device via SSH. So a service like ngrok, okay? You connect your Raspberry Pi with ngrok, which is a SSH tunneling service. So you can connect to the Raspberry Pi remotely. And if it happens that someone connects any kind of USB or HDMI device to the Raspberry Pi, it simply, let's say, deletes the source code from the Raspberry Pi. And again, when you connect through SSH, and you enable, like you say, okay, I want the code back, you know that the device is secure, it again pulls it from Git, so it works again normally. So that would be a hack, so for me, how it worked.
Okay, yeah.
Maybe there's better ways. If someone's more experienced, I would like to hear.
Definitely sounds like a hack, but if it works.
Well, I don't know. It seems a bit unsafe. Like you would damage the product that way, and so I mean, users, the clients, the end clients, they're, well, let's not call them dumb, but they do silly things. Like they're gonna experiment. They're gonna plug in USBs, and they're gonna call and complain that stuff is no longer working. So maybe an alternative solution might be a bit better.
Sounds a bit dangerous, but
That's why it's good, like tracking. You can like track what's happening. You can like track every single input and output device, and you can know if someone tried to do something. And then they can't complain. You just say, "Hey, dude, why are you messing up with my device?"
it was in the
Don't
manual.
touch
You
it.
can't do that.
Just don't touch it. It's not in the user manual. Yeah.
Okay.
So yeah, thank you.
All right, Duje. Thank you very much for your talk.